for the invitation, for giving this talk. And I'm happy to be here and to present some of my recent works with students and also collaborators about increasing labelings in trees and some more constraints than that only increasing as usual in analytic combinatorics. So the first idea of the model we want to develop is the idea of evolutionary tree given by Darwin in the 19th century. So on this tree that it picture out, then at each internal node, there are some distinction between two species of animals or something like this. And there is some kind of chronology, and you see at each level there are some bifurcation and species that distinguish. And nowadays the pictures are more detailed, and here you get some kind of big evolutionary tree given by Heisenberg in one of his papers in 2028. And as you can see, there is an ancestral node here at the beginning, and along the time there are many bifurcations, and at some time fishes distinguished from mammals, something like this. So at the moment we are here, so the leaves of the tree are the animals that are today on the earth. And if you are looking to the common ancestor of two leaves of two animals, you know when the two species distinguished. And there are all other visualization of such evolutionary tree that are done automatically. And here you can see that almost all bifurcation nodes are binary nodes, but this was not already the case here. Here, for example, we have some kind of ternary nodes or with nodes with bigger varieties, but there are not many of them. And this is an important fact that we would have to reflect in our model. So now I will just recall some history, evolutionary trees, and what we are able to do with analytic combinatorics. And then I will go back to varieties of increasing trees that we are now well, we know well them how to describe and how to analyze them. And after all, I will define some kind of growth processes in order to build evolutionary trees. And I will use 3 parts of my talk in order to enrich these growth processes and to develop the deepest model that I can develop. So for the talk, I will especially have a look to enumeration properties, and I will not focus to properties of the model in itself, but in the papers that I will give you have some properties of the trees also. So for the first tree that could be an evolutionary tree was introduced by Schroeder in the 19th century. And in fact, the internal nodes are of arbitrary out degree, and only the leaves are counted in the size. So nowadays, in our analytic combinatorics group, we are used to specify such kind of trees in that way. So a Schroeder tree is either a leaf that is counted by the mark Z, or it is an internal node, but the internal node does not count in the size, so we do not see it in the front of the sequence. And then you have a sequence of children, and the sequence is at least with 2 children. So here you have a tree that belongs to this family, and the root here, for example, is of variety 2. This node is of variety 3, and the black bullets that are leaves are counted in the size. And now, using analytic combinatorics, we have the classical symbolic method developed by Flageolet and Cedric. And we turn from specification, we translate it into a functional equation satisfied by the generating series associated to the class of trees. So the generating function here is ordinary because the tree is not labeled. And so S of Z is the sum of Sn times Z to the n, where Sn is the number of trees of size n. So with n leaves. And using this generating series, we can translate this specification directly to this functional equation. So the Z corresponds to the Z, or plus a sequence starting at 2, so of Schroeder trees, so S squared over 1 minus Z. Okay, and now using analytic combinatorics, we are able to solve explicitly this equation, and we see that, for example, S of Z is algebraic, and we can compute its first element, we can get the asymptotic behavior of Sn, and so on and so on and so on. So this sequence is really well known, and that was the first evolutionary tree introduced in our context of classes of trees. But if we depict big trees and if we zoom in here, for example, we see that there are many nodes that have a big arity. So here, arity4, arity5, arity4. And in the previous slides where I gave evolutionary trees given by biologists, these nodes with a large arity were not so much. So this is a first failure of this model. And furthermore, if I try to organize it as a circular representation using Graviz, due to the long trunk of the tree, Graviz is not able to represent it nicely, properly as a circular representation. So probably this model is not the best one that we could have for evolutionary tree. Okay, so, and in fact, I say that we have no temporal steps. So we could say that each internal node corresponds to a temporal step, but we have no notion of levels because we are used to put all the nodes as top as possible, and so the temporal steps are not well defined. And so in the literature, there are some new varieties of trees that have been developed in the 90s in the sense of variety increasing trees. And going from non-labeled tree to labeled tree, we have to shift from ordinary generating function to exponential generating function. And so now we are in the context of labeled trees. So Tn is the number of trees, and we divide it by n factorial in order to obtain a series that could be analytic at 0. And now in this context, we are able to define trees. And for example, here, if I define the binary tree, here I am counting the number of internal nodes and not the leaves. So we have a leaf of size 0, or we have an internal node Z, label product, and two children with a label product here. And this translates into this equation. So this is for the labeled model. But what I want to introduce is the increasing labeled model. And so we are able to specify such kind of structure using Green's operator. So now we have two labeled classes, A and B, and we want to specify one more constraint on the product of A and B. We decide that the smallest label appears in the component from A. So, okay, when I use this product, I say I consider all pairs of elements, one component from A, one component from B, and the smallest label given in the structure is for the component from A. And using this operator, we can obtain some translation into integral equations satisfied by the generating function, the exponential generating function. And now I can here define some kind of increasing binary rooted trees. So an increasing binary tree is either a leaf that does not count for the size. Then you have a node that corresponds to the root of the tree. And the second component is a pair of two children. And here we constrain this object that the smallest label belongs to this class. So the smallest label is for the root of the tree. From this specification, we can translate it into an integral equation satisfied by the generating function here. And in fact, if we differentiate it according to z, we obtain some differential equation. B prime is 0 plus b squared. Okay, and we can also define some kind of general rooted trees like before. And just two examples. So here I have the classical label product. So all the labels from 1 to the number of atoms, some 10 in these examples, appears exactly once. And there is no order constraint for these binary trees. But if you are interested in increasing binary trees, then we know that the root gets the smallest label, so 1 here. And then it is a classical label product between two subtrees that are increasing. So this subtree is increasing, 4, 9, 4, 6, 7. And this subtree is increasing, but the labels are just separated into two parts according to the size of the subtrees. So here we say that this tree is increasing, and if so, each label appears exactly once, and if you go from the root to any leaves, you just see a sequence of strictly increasing integers. So this is well known for years. And just some pictures. So for the moment here, I depict large label trees. So these have still a long trunk. This is another one. And if we go to the class of increasing trees, we see already that the trees have a depth that is much smaller. And now we also see that GraphViz is able to give a better representation of a circular representation of the tree. And this seems to be typical. I have uniformly sampled trees of size 100 here, and all of them seems similar. Okay, and so all this work belongs to the classical paper Varieties of Increasing Trees, written by Bergeron, Flageolet, and Salvi in '92. And they study many classes of increasing trees in this context. They gave the differential equation satisfied by the generating function, and they were able to explicitly solve some cases and to prove many properties of these trees. Okay, so we could apply this method in order to take Schroeder trees whose leaves are counted for the size and where we increasingly labeled the internal nodes. So the tree structure is a Schroeder tree. The internal nodes are increasingly labeled. We have uniqueness of each label, and the size is the number of leaves, sorry. And now, in order to represent it as a phylogenetic tree, we can use some kind of representation. A hedge as a length that is the difference between the two labels that are at its extremities. So for example, this hedge would have length 4, and then we strengthen the tree, and we obtain some kind of temporality, some kind of chronology along the branches. So now go back to analytic combinatorics. So now we have two atoms here. We have atoms that are leaves that do count for the size, and we have atoms that are internal nodes that are increasingly labeled. So the specification here is with two kinds of atoms, either a leaf or an internal node that gets the smallest label, and a sequence of at least 2 children. So using the symbolic method, we can translate it into an equation satisfied by the bivariate generating function of S depending on S, Z, and U. And in fact, if you are just looking to the size as the number of leaves, we can at a moment put 1 for U and forgetting all possibilities for U. But we could do this and study this tree, but I want to have some more rich model to define evolutionary trees. So I will try to introduce another way to develop my increasing trees for Schroeder trees. And to do this, I go back to the classical model of recursive trees that are well defined in Michel Drimota's book. And in fact, here I focus on plane-oriented trees, so the children are ordered from the left to the right. And these recursive trees, I can define them using growth process. So what does growth process mean? So in fact, I have a tree that is built at the moment, and I spent 1 unit time more, and I observe that one new node appears. Okay, so we start with with a single node labeled by 1. And now I have a process that I iterate through the time, and at step L, I select a node, and I attach to it a new child node labeled with this value L, that is the step number, and among its sequence of children. So for the moment, I have a single node here, 1, so I must choose 1, and it has no child, so I have no possibilities. The second node, 2, is just like this. And the next time, I have to choose either 1 or 2, and then I will have a new node 3, and if I have chosen 1, I could put 3 to the left or to the right, and I have chosen 2, I have to put it in the bottom. So for example, here I just take the right possibility for the child of 1. And then I have a 4 that appears here, and so on and so on. So this, I want to mimic this process in order to label Schroeder trees. So this first model of strongly increasing Schroeder trees, this has been developed during the thesis of Mehdi Neima, and it was in collaboration with Olivier Bodini and Cécile Mayer. So I have my increasing Schroeder tree, and now I want to define some way in order to let this tree grow. So now I start with a leaf, so just a bullet, and I iterate the process. At step L, I select 1 leaf, and I replace it by an internal node label with label L, that is the step number, and I attach it to it a sequence of at least 2 leaves. So at step 10 here, for example, I select this node, and I put a new internal node labeled by 10 with 3 children. And now I can let my tree grow like this. And now, in fact, I am able to specify this class of trees in this way. So an increasing Schroeder tree is either a leaf that counts in the size, or I have already built a tree. I point one of the leaves, and then I replace it by an internal node labeled by the iteration step, but this is hidden here in this process. And I attach to this new internal node a sequence of at least one atom, because I reuse the pointed leaf that I got there. So from this specification, I can translate it in a differential equation. because this operator implies differentiation, and I obtain this equation. But here we have to be careful because these leaves are not labeled. So we are in the context of ordinary generating function. So if we study this equation deeply, we can see that this corresponds to ordinary generating function. And so this is not analytic at zero. So in order to analyze it, we have to do some kind of rescaling or something like this. But it's not necessary, because if we are counting the first element, in fact, we see this sequence, and this sequence looks like half the number of permutations. And in fact, we are able to put these trees in bijection with the half of the permutations that are permutations starting by the one appears before the two. And these are the permutations we are interested in. So there is no work in order to obtain the asymptotics. And if we have an equality, Sn is equal to the half of n factorial due to our bijection. So this was easy. So we try to enrich our gross model. As you have seen before, when I have longer edges, it's here for 2 to 6, I have 4 units. We see that the levels, at each level, there is exactly one internal node. We cannot have two bifurcation at the same level due to the strictly increasing labeling. So we have no repetitions inside the label, so we cannot have twice at the same level an internal node. And this is a restriction that we want to remove. So we have introduced another model where we allow repetitions in the labels. And so using this kind of tree, we have no classical analytic combinatorics tool to specify such kind of structure, because classically we cannot have repetitions among the labels. But using our gross process, it's not easy. It's not hard to have repetitions. Instead of selecting exactly one leaf, we select a subset of leaves. So for example, here I select this leaf, I select this leaf, and I replace this one by 8 and 3 nodes, and this one by 8 and 2 leaves. So I have just adapted a little my gross process, and I am able to specify trees with repetitions. And once again, we can specify the process, the iteration, such that a tree is either a leaf or it is a tree that is already built, and inside this tree, the leaves are kept as a leaf or are replaced by a sequence of at least 2 leaves. Okay, and in fact, if I am doing this without this minus s, then I have the possibility that at an iteration I have no replacement, because if I always take this z instead of this. At the step level, at this step, I will have no replacement, and so there will be a lack in the labels, and I don't want to have lacks in the label. I want to have a consecutive, all integer in a consecutive range must appear. So I remove this f of z to forbid the case where no where no leaf is replaced. If I do this, I can compute the first elements, and once again, I have chance. I recognize ordered Bell numbers. So we can put these Schroeder trees in bijection with order set partitions with 1 element less. And so for free, we get the asymptotic behavior of Sn. And this asymptotic behavior is interesting. In fact, here we recognize n factorial over 2. This was the number of trees without repetitions. And now we have a bit more possibilities to label our trees, because we have we have repetitions that are possible. And in fact, here we have an exponential growth that is positive, that appears that increase these numbers of strictly increasing Schroeder trees. And in fact, this kind of pattern will appear in other models, as you will see later. So, and if we depict the two models of tree, in fact, in the same scale, here I have no repetition, here I have repetition. In fact, the fact that having repetition gives trees that are more compact, because on the same level, according to the root, we can have several nodes labeled with the same value. So that's what we could what we wanted. Okay, I want to enrich once more my process. And in order to obtain this, I come back to my port model. And this is a work that we are working on at the moment always with Olivier and Mehdi and with Alois Panolza. Okay, so we go back to our ports, and in fact, here I have some anchors, and the next time I will choose one anchor, and I will put the label 8, right? So that was the first process. And now I modify this process. Instead of taking a single anchor, I select a non-empty subset of anchors. So if I have a tree of size t, the number of anchors here is 2 times t minus 1. So here it's 14 minus 1. We have 13 possibilities. Okay. So for example, here, for the one I have a single anchor, I choose it and I replace it by a sequence of 3 times the label 2. Next, I have 4 anchors for 1, 2, 3, and 4, 3 anchors for the 2, and I choose this anchor, this single anchor, and I put the label 3. Here I've chosen this anchor and this anchor. Here I have taken a sequence of 1 element, a sequence of 2 elements, and now I am obtaining some parts with some kind of parts with repetitions. I can continue so on. And now I want to specify it. So again, T, the generating function, is an ordinary generating function because here, the fact that I have numbers does not interfere the way that I am growing my tree. So this is a specification in the ordinary case. So either a leaf or either a node or the nodes and the anchors are modified. So here I have the squared is this to the 2, but I have to remove 1. So I get this prefactor here. And finally, I have to remove the case where no addition is done. And I can compute the first elements. And now it's annoying because this sequence is not in OES. So I have not for free the asymptotic behavior. So now we have some more to do. And in fact, I will give you some key arguments in order to give you an intuition how to get such kind of asymptotics for these trees. And again, before giving these key arguments, I just want to highlight 2 things. So here I have a prefactor, and this prefactor is exactly the number of ports. So the recursive trees that are plain and without any repetition. And then when you authorize some repetition, you have this extra factor that is exponential and with a polynomial modification also. But in fact, this factor is much less than this one. This is of order factorial. This is only of order exponential. Okay, how do we get this from this specification? So the first thing is that in our specification, everything is formal. So we first normalize the sequence. And here we normalize it by a prefactor that is the inverse of the number of ports. Okay, so I define this new sequence Bn to be my first sequence normalized by this factor. And then I can obtain a recurrence relation for Bn that corresponds somehow to this one that is normalized, to the one of t that is normalized. And in this model, I can build a tree of size n according a tree of size whatever you want, and times a number of possibilities how to graft the sequence of new labels. But you have also this decreasing factor that is k factorial. So seeing this relation, in fact, we denote this factor as gamma nk, and this factor will be the key element in order to understand how this new sequence Bn behaves. So now we study deeply in detail this gamma n, and we obtain a lower bound for it that is like this, and an upper bound for it that is like this. And the upper bound and lower bound are correct for all positive n and k smaller than n. And the key here is to note that the two first terms, when n becomes large, for the lower bounds are equal to the two first terms of the upper bound when n gets large. Okay. Then, using the lower bound, we define a new sequence B over underline. And we use the gamma underline, so this lower bound, and we define it, and we can define also an upper bound. And in fact, we can easily define two new sequences, underline Bn and overline Bn, such that the interested one is in sandwich between the both bounds. Once done, we go back to our sequence here, but for the lower bound. And in fact, the recurrence relation can be translated into an ordinary differential equation satisfied by the generating series. Here it is linear of order 2, so we are able to solve it. And go back to chapter 7 in Flageolet-Sedgwick in the context of ordinary differential equations. So there are many technicalities. We have to consider some kind of indicial polynomials, and we have to check some conditions on it. But once you have done all the work, we can derive the asymptotic behavior of underlying Bn. And in fact, much interesting, we obtain that the exponential term and the polynomial terms are just depending on this prefactor and this prefactor. And the other prefactor here does not intervene in this factor, but just in the constant. And before I mentioned that my upper bound had exactly the same two coefficients here. And in fact, these two coefficients defines exactly the two first factors here. So my upper bound will behave like this with another constant. So I am now able to prove that Bn is a big theta of this factor here. And if you want to obtain the equivalent asymptotics, you have a bit more details and to be a bit more careful, but we can solve it also. And now I will apply this to more powerful growth processes. So this in this work, I was working with Olivier, Bernard Kittenberger, Stefan Wagner, and also with Alexandros Zing. I think he's here also. Okay, so now I want to enrich my process. So I defined a new function phi of u that is a sequence starting at 2 of phi I u to the I. And I define this function as a colored degree function. For example, if I take this polynomial, I can interpret it as I have one type of binary node, I have two types of quaternary nodes, and I have five types of nodes of RT5. And the types can be represented as color, for example. And I have a second parameter that is a subset of n without 0, okay? And this corresponds to the number of occurrences I allow for each label. So for example, if I take the small subset 1, 3, 4, this means that I can either have one occurrence, 3 occurrences, or 4 occurrences for a label for internal nodes. Yes? This one? This is the colors for internal nodes, and this is the labels that I will put in my internal node. So this is distinct. Because for the moment, I don't want to have unary nodes in unary internal nodes. We are able to give results that are not consistent with this because we have some technicalities that appears, and so for the moment in my internal nodes I forbid unary nodes. In fact, at the end I have just a picture, and you will see where there is something strange that appears in this case. Okay, so for example, in few minutes, so I take this colored function. So yeah, I have two kinds of binary nodes and two types of ternary nodes. The colors are white and gray for both internal nodes. So first, I start with a leaf, and I choose one integer where phi k is positive, so either 2 or 3. And I take one of the color, white or gray. So for the moment, I have chosen this node, and I take a binary node of white color. Okay, I get these 3. I continue, I select one leaf. With this replacement, I obtain this. But here I can choose a subset of leaves. And now I have chosen 2 leaves here, and I replace them with a binary node and a ternary node, either with color gray or with color white. I obtain these 3, and I can continue like this. So this is the first way to interpret my new model, okay? I allow to have colors inside the internal nodes. The colors are well defined. So for the moment, I have a finite number of colors, and I have here a finite number of varieties. But in fact, in my previous slide, I did not give such kind of constraint on the parameters. So now I take another example. My colored function is this one. It starts like this. And here you recognize almost the Catalan series where I have removed U1. And this is exactly the series for Catalan numbers without U. And I allow to have as many repetitions as I want. And now, how can I interpret my growth process? Oh, I start with a leaf like before. I choose it, and then instead of choosing one type of node and one color, I choose a tree shape that is encoded as a binary tree here. So for example, I choose among nodes of Arity4, the tree with this shape. This tree has exactly 4 leaves, so it belongs to my class denoted by 5 times u to the 4. In fact, I could have 5 other shapes of binary trees here. And I replace the node, the leaf, by the tree shape, and I allow, and all the internal nodes are labeled by the same step label. So here I allow this head for my tree. Here I choose this subtree, and I replace it by a ternary shape of this shape. And every internal node is labeled in that way. And here I take a subset of size 2. And for the first one, I take a shape with 2 leaves. For the second one, I take a shape with 4 leaves, and with these shapes. And so I can grow my tree in that way. And now there is something that I was not able to do before. Along the same branch, I can also have repetitions in the labels. And this was not possible before, because before I was replacing a leaf by a single internal node. And now I replace it by a shape, a tree structure. So now in this enriched model, we can obtain classical increasing trees. We can obtain the last model that I just described here. So I have 3 shapes with the same labels here. We can obtain strict monotonic. So along the sequence, you have no repetition. Or we can have some monotonic trees where we have label repetition, weakly increasing, and we have repetition anywhere in the tree. And all these models are available through this growth process. And now the main theorem for this process. So I have just a technicality property here. Phi should not increase too fast. But in fact, this too fast is it's really a technical property. Just before I take phi n to be Catalan of n, so this is 4 to the n. This is much smaller than this possibility. And I just denote by m the smallest possible, oh, this is a capital R. So m is the smallest value of R. And now, by supposing this condition, I am able to obtain the enumeration value that enumerates the number of trees with n leaves in the enriched model defined by phi and R. And its value corresponds to factorial n. Then you have an exponential term depending only on phi2, n rho, and I will define rho just later, but not with other values than phi2. And the polynomial terms depends on phi3 and phi2 squared. So in fact, and you have this rho, and this rho, in fact, corresponds to the function where you take all possibilities for R, and you define the exponential generating function for these coefficients. And in fact, if R is equal to n minus 0, then when you solve it, you obtain the log of 2 that you obtained just before, because here you have the exponential generating function. And so what is interesting in this asymptotics is finally that the main trees you obtain have almost all their nodes of Arity2, and the polynomial terms that perturbate a little bit these exponential terms does only depend on with nodes of size 3 and nodes of size 2. And finally, the arities of the other possible internal nodes do only modify the constant factor of the asymptotics. And I just conclude. So here I have some possibilities to specify a growth process and to obtain some of our papers, but also other papers. This one is a paper in algebraic combinatorics. And this one was given by biologists some years ago. Here you have the literature, the references I used. And so thank you very much for your attention.
Does anyone have any questions for Antoine? Svante?
Probably it's natural for me to ask what happens if you know take one of your classes and specify the size with the MD say and take a random subtree. I guess that for your method you can answer various questions about that. Can you say something, for example, about the average height of the tree or some other properties?
Okay, so for some of the models, we have looked to the depth of the tree and using especially the paper with Cécile, this one with strict monotonic Schroeder trees, using a probabilistic method tools, we were able to prove that the trees is of depth log n. But for the moment, we are just at the level of enumeration asymptotics, and so we have not looked in details to properties of the structure. But in fact, it's natural to have looked in this direction for the next years. Thanks.
Other questions? Cyril, I think you had one. Yeah.
So with respect to the question, so you said that at the end we will see.
Yes, but in fact. No.
Oh no, there is.
In fact, if you you will see on the slide, there is here a big tree that is depicted, and that allows internal nodes of RET1. And in fact, you just in fact, you will see that all the leaves are at the same level without having stretched the edges. Because in fact, in this, when you allow us to have a unary nodes, at each time, 1 time over 2, the leaf will be replaced by a unary node. And so the structure of the tree is completely different from the other cases, and it does not behave like logarithmic depths anymore. And so we have some asymptotic results, but they are completely different from this one.
You know the typical exponents that you have.
Yes.
When you do the asymptotics of the differential equation, you have this indicative function gamma,
yes,
on the slide 25, which you get as okay, you know that it is existing, you can get some digits of it.
Yeah.
But do you have a kind of first form or at least implicit equation that gamma is satisfying?
It depends to the model. For example, for the simplest model with ports, with Alois, we were able to obtain some explicit form in let's say with an integral formula. But usually we are not able in the globality, in the more enriched model, we have no closed form for the moment. We just know that we are able to prove that it exists. So we have a theta, we have an equivalent. We have not only a theta convergence, but we have no closed formula.
There was a question here. Yes, please.
Yeah, a semi-mathematical question. And that is that Schroeder's model was modeling evolution.
Yes.
It was a while ago. Do you know how well the data that we have now matches the prediction one would have thought? Now, I realize that his model probably does not include anything to do with mass extinction.
No.
Yeah.
Yes. Yes. Right. Yeah. Yeah. Yeah.
So have you heard?
In fact, the start of the work was to say, at the moment, biologists and bioinformatics people are using much more evolved processes in order to modelize their tree. And we wanted to go back from the simplest model and to enrich it step by step in order to be able to analyze it completely using our tools. And surely our model is not sufficiently powerful for biologists at the moment. But so, and for example, extension is not taken into account, and many other characteristics are not taken into account. But in fact, I think that beyond the evolutionary tree introduction, I think that our enriched model is interesting to modelize other possibilities, for example, of structure in computer science and something like this. Thank you.
Jim?
The same question slash comment as Svante Jansson, but I want to push it even further, which is that, so you've introduced growth processes as a way of describing these various classes of trees, right? And presumably the same probabilistic model that would give uniform distribution after, for trees of a given size would also have a corresponding probabilistic description for the growth process. And I think it might be interesting to study the process, that is the dynamics of this, and not just the statics for a given large value.
Yes, that's true. That's the next step of this kind of combinatorial tool. Now we have to look to probabilistic approach in order to obtain some kind of correspondence, and then to obtain maybe results, properties from another point of view, and that we are not able to obtain easily by combinatorics, for example. And surely this is the next step to have interests with probabilists in order to solve such kind of problems.
Do you know, for these various models, is it a fairly simple probabilistic description of the growth process that would correspond to a simple probabilistic description of for a fixed value of n?
So, for example, at the moment here, if we want to develop some kind of random model, we have the uniform random model, combinatorially meaning. So each tree appears with the same probability. But if we use some kind of random process, I'm not sure that we can easily obtain such uniform distribution at the end. I don't know.
Sort of question.
Yes.
It would be interesting to see if you can, putting some sort of probabilistic model on the growth process, what that would lead to as an alternative to the uniform distribution.
Yes, that's a very interesting question, I think. Yes, thank you.
Okay, one last short question. Yes.
Yes. Because here you have ordered set partition of size n-1, and so here you should have n-1 factorial, so I divided by this. Oh, could you please repeat the question? In, in fact, this corresponds to trees without repetitions of size n. And when we allow repetitions, we have another bijection with order set partition of this size, so n-1. And I think that these numbers are counted asymptotically by this formula. But maybe there is some typo.